Page 4. Now, the second law of orbital motion. This one can be a bit wordy, so I like to break this down into something as simple as possible. And to remember this, it's not even a sentence that makes sense all by itself. In fact, I don't even think it's a complete sentence at all. But it helps me remember what's going on. So I'm going to say equal area in equal time. That's how I remember this second law of orbital motion here. And so let me show you what this means. I'm going to create my elliptical orbit. And I'm going to focus there. So that's where the sun would be located if we have a planet. And here's the deal with this guy. Let's put the planet, I don't know, let's start him here. So here's the sun, and we're going to track the planet. And here's the deal. We're going to track the location of the planet for a certain amount of time. And what we're going to notice is that, let me draw an imaginary line here. So we're going to start with the planet there, and for a certain period of time we watch as the planet orbits, and let's say we stop watching when the planet is here. And I'll draw an imaginary line there. So what has happened is that the planet, if you watch this imaginary line, the planet has sort of come around this way, and this line between the planet and the sun has traced out a certain amount of area. Now we don't have to figure out what that area is, but you can see, right? There's an amount of area there. And so here's the deal. What Kepler figured out was that if you track the planet for the same period of time when it is somewhere else in its orbit. So let's say we start tracking the planet while it's here, and for the same period of time it's going to end up there. And what happens is this: imaginary line and imaginary line. And let's look at this area. What Kepler's second law says is that the surface area, well, the area traced out by the planet in this period of time in this part of its orbit is the same total area that is swept out by the planet in this side of its orbit, or any side of its orbit. The equal area in equal time. Now here's the deal. You look at this and you say, well, maybe that area is equal to that area. Okay, fine, Woods, I'll buy that. I'll accept that. But what's going on here? The planet sure looks like it went a lot further here than it did here. And you would be absolutely correct. Good job for recognizing that. If it's going to travel more distance in the same amount of time, so really think about this. There is a change in position from here to here, and there's a certain amount of time. Well, there's a change in position here to here as well. So change position for 1 and change in position 2, but time is, and you gotta say, look, I gotta recognize this change in position is much greater than this change in position. I have to recognize that. But the time is the same. So therefore, what's going on? Well, the speed of the planet must be changing, right? Speed of the planet in area 1 versus area 2. So here's the deal. Here's the brilliance of the second law of orbital motion. Equal area in equal time, yes, that's an easy way to remember this. But why is this important? Because it says that the planet is moving faster when it is closer to the sun and slower when it is further from the sun. That's the implication, and that's what makes this an important law. As the planet gets closer and closer to the sun in its orbit, it's speeding up. And as the planet gets further and further away from the sun in its orbit, it is slowing down. Now, this is before Isaac Newton and his laws of motion. This is pretty groundbreaking. And this is before ideas of energy that we're going to actually study later on. And for Kepler to come up with this, the guy was putting in years of work into this, trying to realize this relationship. Pretty phenomenal stuff. So this idea comes back in physics and astronomy quite often later on. Now, the third law of orbital motion. Let's get to this. If that wasn't wild enough, just wait. Third law of orbital motion. Here we go. One way of looking at this is by comparing the orbits of two different objects that both orbit the same thing. So you might think of two planets that both orbit the same star, like Earth and Mars, if you like. Any two planets orbiting the same star, or any two satellites orbiting the same planet. It doesn't much matter. But you can use this to compare those two objects. So I'm going to do a quick diagram here. And I'll use circles. It's just a little easier that way. Let me see if I can do this with this guinea pen here. Let's try this guy. Okay, not bad. I'll show it up. Put the center in there. I don't know, give or take, right about there. And that's kind of interesting. It actually doesn't look circular in the image, but that's okay. What we have going on is the sun in the center, just for our example. And we can say we've got planet A and we've got planet B. I'll just put planet B here. And planet A is this distance away from the sun, radius of A. Planet B is this distance away from the sun, radius of B. And the third law is looking at the radii, the orbital radius here. But it's looking at something else. Kepler, after lots of toil, lots of work, looking at the math, looking at the geometry, was able to figure out that there's a relationship between the radius and the orbital period. So orbital period, remember, is capital T, and it is just a time that it takes to complete one orbit. So for planet B, it's the time it takes to go once around in that orbit. For planet A, it's the time it takes to go once around in this orbit. So there's a period, and the period of A divided by the period of B. That's a ratio. And when you do that division, you just get a number. What Kepler figured out is that ratio between the two periods of the planets is sort of related to the ratio of the radii of the two planets. Now I say sort of related. I did not put an equal sign in here yet. There is an equation that we can make from this, but we got to be a little careful about this because it's not so straightforward. And this is why it took Kepler a while to come up with this. He didn't invent this. It's just Kepler seeing this relationship mathematically in all of the data that he had. And so there we have some exponents. So here's how you read this. The square of the ratio of the periods of two planets is equal to the cube of the ratio of the orbital radii of the planets. Now, I don't want to have to write that down in words right now. I'll say it one more time. The square of the ratio of the orbital periods is equal to the cube of the radii of those same two planets. This is one way of looking at Kepler's third law of orbital motion. Now, there's another way I want to show you, because it's going to come back to us. We're going to kind of hate to use the phrase "come full circle" here, but there you go. Another way of looking at this, and I'm not going to get into the math why this works. If you don't want to compare any two planets, you just want to look at a single planet. The square of the orbital period of any planet, or any moon, or any satellite, I'm not going to put an equal sign, I'm going to put this, it means proportional, is proportional to the cube of the radius, the orbital radius of that planet. So this is not an equation. We are not equating the two. There's not an equal sign. But we're going to see this come back to us. And in fact, if I wanted to make an equation out of this, I'd have to do this. I have to say that, and then I'm going to put a capital C. I don't want to use capital C. Let me use just big X. Big unknown, right? So this guy isn't just a big unknown that we don't know what it is, but we have to put it there to make an equation. Now don't worry too much about that. We're just showing that the square of the period of a planet is proportional to the cube of its orbital radius. So for Kepler, in fact for anybody else, this would not have been an easy relationship to see. And it is an interesting relationship, but it wasn't until Isaac Newton described his universal law of gravitation that this relationship became really useful. That Kepler's third law became important. So for now, those are Kepler's laws of orbital motion, and we'll look at some more interesting stuff later on. Thanks for watching. I'll catch you next time.